fact, okay, because somehow, I will discuss, in fact, mainly the work of, yes, the pointer does not work, right? Okay. So it's part of, so I will somehow, in fact, explain the big picture about Vincent Placier's works, which was a PhD of mine and Eric, and also with Maxime Vonneau, which was a postdoc at some points, and now he's at Criteo, and also, it's also joint work with Nikita Koltoyevsky, and yes, that's okay. So, just a brief summary of this talk. So, okay, I will start by basic motivation of my work, mainly on this kind of federated Bayesian inference that we didn't, in fact, heard yet. Then, okay, I will provide you some brief summary of two federated Langevin samplers. That's okay. We have, in fact, promotes and develop, which we name QLSD and FALD. And okay, I will end with exactly the main content of this talk, in fact, which was in the abstract about personalized federated learning, and okay, with an algorithm which we name FET-POP, but in fact, Sam already introduced a bit about this topic, and it will help me a lot in introducing this methodology. All right. So here, in fact, I'm basically, in fact, aim to make uncertainty quantification. So here, I suppose that I have a probability prediction. Based on this probability prediction, in fact, people are interested in making calibration on your prediction. So here you can think about test your model on the likelihood, or using Breyer score, or expected calibration score, which in fact I don't provide you the explicit expression, which is a bit very long, and I don't have much time. So, but basically, in fact, it gives you the discrepancy between the confidence of your prediction and the real accuracy. But here, okay, all this uncertainty, all this score, in fact, are based on your model. And here, what I'm interested in is to construct this model using Bayesian inference. So I will not debate about the use of Bayesian inference for deep learning, because here, in fact, I'm just focusing. I want to apply Bayesian methodology for constructing my prediction, my probabilistic prediction. So here, just for the notation, I suppose I set a model, on my label given my features, parameterized by theta, which is specified, let's say, by a likelihood. I choose my favorite prior, and given my train sets, I can define now my posterior, which is simply proportional to my prior, and times the product of my likelihood at my given data. All right. And then, based on this prior, I can define the predictive distribution associated with my posterior distribution, which is just the integral, of my model against my posterior distribution. And somehow we can see that you average your prediction given your posterior knowledge of your data. And that's somehow the rationale behind all the Bayesian inference. And here, you can see that the main challenge is to sample from the posterior distribution given the data, and an algorithm to sample from a distribution which is non-optimative constant, which people in the room work a lot, is a Langevin algorithm. So let's say that now I denote by minus log of pi u. It's what I call a potential, which is a term which comes from physics. But here, in fact, I can decompose my function u based as the sum of functions. So v0, in fact, stands for minus the log prior. And now, I can take a sum over my data of vi theta, and just vi is, the log minus the log of L theta of yi given xi, where yi is just one given data point. Now, based on this notation, I can introduce you the Langevin algorithm, just to try to get approximate sample from this posterior. So here I just define a Markov chain theta L as, theta L plus 1 equals theta L minus gamma gradient U theta L plus square root 2 gamma ZL plus 1. So here gamma is my step size. And so it's, you can see this. In fact, the motivation behind this scheme is that the discretization of the Langevin dynamics, that you know that it converge well to the posterior. But still, you have some bias. And still, you can analyze, in fact, the explicit convergence band for this scheme to pi. And also, you can replace the gradient by some stochastic gradient as SGD. All right. But here, now, in fact, I want to apply this methodology in a federated context. So on each client, I suppose that I have some local data sets. So here, it should be not J in dk, but K. So I have, in fact, individual data sets. And on each, in fact, client, I have nk data. And based on this local data set, I can define what is called local posterior. So it's just the posterior distribution associated to each client based on their data. All right. So here again, in fact, I could decompose also the potential as a sum of individual potential. All right. And but here I want to define a global model across all my agents. And Bayes' formula just tells you that, in fact, the a posteriori distribution of your global model is just proportional to the product of the local posterior. So here, my main objective here is to try, in fact, to adapt the Langevin methodology to this federated context, akin, in fact, what is done in federated learning, but for stochastic optimization. All right. Just for somehow a teaser. So in fact, there have been in the literature other approach, to try, in fact, to get to construct some sample from this global posterior, especially, in fact, with what is called Bayesian fusion. Or also, in fact, it has been proposed to, in fact, trying to get a sample from the local posterior by constructing, in fact, Wasserstein barycenter based on this sample. And in fact, we have proposed in a recent work with a PhD student of mine, Maxence Noble, in fact, a scheme to try to construct, in fact, Wasserstein barycenter based on sample from pi_k. So if you're interested, we can discuss it later. But I will not discuss this work because it's very technical and so on. But here, I want really to focus on the development of Langevin sampler for sample from this global posterior. So here, in fact, the main, in fact, rationale and of this type of scheme is that as, in fact, usual federated stochastic optimization, so I have a current iterate tk, which will be, in fact, my current, let's say, sample from my MCMC algorithm, my federated MCMC algorithm. The server sends back, this sample, an approximate sample theta k to the user. Now, in fact, the user can perform local operation, and based on this local operation, they send the results to the server to update the next parameter theta k plus 1. And based on this, so the server now have computed the update theta k plus 1, and the theta k plus 1 is sent it back to each client, and again and again. And somehow, in fact, it summarizes the scheme that we have developed, the federated Langevin sampler that we develop akin to what is done, in fact, as I said, to stochastic optimization. So here the first scheme that we suggested. So is, in fact, somehow the same as in quantized SGD. Compute, in fact, okay, so I will be very quick then. So the client, okay, computes their gradients associated to their data. They compress the gradient and send it back to the server, which in fact perform a local step of compress SGD. Okay, but here you just add the Gaussian term to in fact use this. So you can see this as a federated quantized name that we put on the algorithm. And okay, the second methodology that we have analyzed is okay, somehow akin to local SGD, where in fact instead of SGD on each client, you perform in fact local launchment step associated with each local potential. Okay. So here now, I really want, in fact, to move on what we have done on personalized FL, because somehow it responds to also some talk. So here, as I said, so somehow on each client, okay, we have some local likelihood. Okay, so what's based on the dataset decay. And here, what we try to construct, so here we have the local, also posterior, based on the local likelihood, but somehow we assume a global model across all the clients. And somehow for personalization is a limitation. And here our idea, okay, in our work with Nikita, Maxim, and Vincent was in fact to introduce personalization by the means of local variables seen as latent variable. Okay, so more precisely, so here we suppose that the local likelihood, okay, the integral is a marginal, okay, of across in fact latent variable which depend on the clients. Okay, so here now I suppose that in fact I have a hierarchical model where in fact the data come from in fact the likelihood of the data depends on a global parameter phi and local variable zk, okay, and I put now, okay, now it's specify my likelihood, and now I put a prior on my local variable zk, and I put a prior on my local variable zk, depending on an extra parameter beta, which are in fact global to all my clients, okay. So here you dissociate really in fact as in some talks. Somehow you have in fact two levels, one which is in fact global and the other one which is local. All right, and here now the parameters that you want to infer, okay, is in fact the global parameter, okay, of the likelihood and the parameter of the prior on the zk, okay. And so here in fact you can see the problem as marginal likelihood. A marginal likelihood problem, all right? And so here, in fact, now the main issue, so if you can write this problem as now a federated stochastic optimization problem, but here, okay, the function fk or fi here is just minus the log of the marginal likelihood, the individual marginal likelihood, okay, based on the data di, all right? And here, okay, just to a teaser, so what is important is that let's say that you have optimized now this function, okay? If you have access now to phi and beta, okay, you can in fact have access to you can use an empirical based approach, and you can also try to sample from the posterior of the local parameter of the local variable zk, and gives you in fact a way to get personalized uncertainty quantification. But now, okay, let's focus on trying to optimize this function. So here, it's, as I said, just somehow a federated, you can encompass this problem as a federated stochastic optimization problem. And here the main issue is that, okay, the function are some marginal likelihood, but okay, you can use, in fact, usual tricks from the field to just write now, to use the gradients of the individual function fi as the integral of the gradient of the log of the data given the parameter times, okay, the local posterior. And now, okay, to get, in fact, NBS estimator of the gradients, you just need, in fact, to ask to each client to get approximate sample from their local posterior, okay, which is personalized, and from this sample, okay, you can get NBS some estimator for the gradient. So here is for beta, but it's also for phi. Okay, just so you end up with the algorithm, the natural algorithm associated with, and just some toy data. So we compare it on a very toy example here. So we, in fact, we compare it to, at that time, okay, let's say a state-of-the-art algorithm, which was FedRep and FedAveraging, which, in fact, so you can see that we were capable, in fact, to get really more accurate estimation for the local parameter on this toy example, which somehow is cooked up to work, okay? And also, so we also had some application for classification, but I wanted really to illustrate this methodology for uncertainty quantification, where, in fact, based on the posterior distribution, the local posterior distribution, we are really able to get personalized, in fact, uncertainty quantification from this methodology. So we use it, in fact, for calibration, so to get personalized calibration error and on MNIST and MNIST and other data. So thank you very much, and if you have any questions.
Any questions? And meanwhile, Praneeth, can you set up? Yeah, maybe I can ask a question. How do these how does the quality of this uncertainty quantification compare with if we pooled and we just trade a standard Bayesian model?
So here you can use, in fact, the data on all the clients also.
I'm just curious if usually in the proofs of these federated convergence, we prove in terms of like the accuracy convergence. Can we also prove something about the uncertainty measures of uncertainty will also converge to as if we were computing on the pool data?
I'm not sure that I understand completely the question. So here is you want somehow to construct a global model and you dissociate somehow.
I'm just curious, like how much does the distributed data hurt for the uncertainty quantification versus if we didn't care about privacy and we just used a centralized method?
So I don't. Here you want somehow you assume somehow some kind of heterogeneity also across data. So here, in this case, it's I don't really see, in fact, how it goes.
I see.